Okay, so we have more examples of calculating rotational inertia using integration. So let's get started. We have this one is a bar, but this bar is not a uniform bar anymore. And we have the origin here, and the bar extends from minus 0.25 to plus 0.75. I just made it up into a 1 meter bar. It sounds nice. And it has a density function. So the density function is lambda. So let me put the lambda on the left side. And this lambda is 0.1x minus 0.05 x squared plus 1.2. All I was doing was to make sure that the density doesn't go to negative at any point along the bar. And we know that we need to do integration. So the rotational inertia is r squared dm, right? So let's get started. Just like before with the uniform bar, first I want to just cut out a piece. Let's just cut out a piece. This is an arbitrary piece, and this piece contains mass delta m. It's finite, and it also has a width delta x, so some mass included here, and its location is simply x. Right here, this is location x in the middle, representing the where the mass is. So I can have delta m. Delta m is approximately equal to lambda times delta x. The approximation is because there's this extends, and the lambda changes across the entire bar. So there's going to be some variation from the left side to the right side of this little piece. So by just taking lambda in the middle, I'm doing an approximation. But this approximation goes away once I do a limit, squeezing this delta x to infinitesimally thin, then we can have that. So this left side, the delta m goes to dm, and we have equal sign lambda dx. Okay, so this is how we can replace that dm in this integration with dx. And also this r is equal to x, right? So the distance from the axis of rotation here, axis of rotation to this point, and this distance is called x. Alright, so we have these two crucial pieces of information to make this integral doable. So let's do the integral. The r gets replaced by x, so x squared, and dm gets replaced by lambda, which is a function of x, just to remind the audience, and then dx. Now, since we have everything in x, we can specify we integrate x from minus 0.25 to 0.75. Alright, so let's plug in lambda. So x squared 0.1x minus 0.05 x squared plus 1.2 dx. So we have 1, 2, and 3 separate polynomial terms to integrate with, right? Just distribute that x into the parentheses. So we have 3 separate integrals. So let's have a new line here. We have one integral is this 0.1x cubed dx, and the next integral is a negative 0.05 x to the fourth power dx, and then the last one is x squared times 1.2. Let's move them around. 1.2 x squared dx. So they're being integrated with the same exact limits, and let's integrate. So that becomes 1/4 x to the fourth power. So 0.1 over 4 x to the fourth power. And here's the negative. Negative 0.05. Now fourth power integrates into fifth power. So this fourth power integrates into fifth power, x to the fifth power. and then plus 1.2 second power into third power, x to third power. So everything will be evaluated in between minus 0.25 and plus 0.75. That's where the bar is. Okay, so you can pause the video and perform the calculation. This will take a little while, but if you use Python, you can define the function and just substitute the function's x value by these fairly easily. Okay, so we're back. After substitution, we have 0.180, and let's use kilogram meter squared as a unit. Okay, so just as a review, how I was able to do this, first I picked this arbitrary cut, right? This arbitrary cut contains some mass, and I turned the mass into linear density times the width of that cut. So with limit of delta x goes to 0, I get dm on the left side and then delta dx. So this is how I turned this part into something I can integrate with. And then secondly, I also took the distance from this part, this piece, to the origin, that is x. So r is equal to x. I replace r with x, and now I have everything that can be integrated with respect to x, right? So I integrated all the terms, plug in the limits, and I got this value. Okay, so let's take a look at a second example. This is a two-dimensional example. So this thing here on the right side is a disk. So it's a solid disk, and we want to know the rotational inertia through the center. Okay, the center being right here. So this x rotation. So we know this answer because we've done this before as a just an introduction. What about this thing? What is the rotational inertia of this? What's the rotational inertia of other shapes? So we have this as 1/2 mr squared. The r being the radius, m is total mass. So since we already have the answer, we just need to come up with the steps to integrate into this answer. So let's assume that we know this. We know ring. Because ring is easy. We talked about ring in a previous video. So the ring is I equals mr squared, right? Okay, so if I take a look at this disk, the disk is actually a collection of concentric rings of different radii, right? So if I take one arbitrary ring, well, I don't know if I can draw this well enough. So let's see, we'll probably put some points here to aid my drawing. Another point over here, point over here, and point over here. So I'm gonna do my best to draw a ring. I think I'm trying too hard to reach those 4 points, so I make it kind of a kinky shape. So I did a ring, but this ring is actually not enough. I'm going to draw another ring so that I have a thick ring. Actually not very thick, but I need this ring to have area instead of being just infinitesimally thin, right? So I need this thing to have an area. Oh, that took a while. Okay, so I have this ring, and this ring has area, so let's shade this ring. Alright, so for the moment, we know that the total mass is m for the disk, and how much mass is this ring then? Well, it depends on the area of the ring, because the disk is considered a uniform density mass. So we need to find the area of this ring in order to see how much mass is in there. And let's first just say we give it a variable, a delta m. This is the mass on this ring. So this little ring will have this delta in rotational inertia, which is delta m times the radius of the ring squared. So let's use a lowercase r, which means that r is going to change with different concentric rings, right? So delta m times r squared. So what I just did was I assumed there's a small ring that's a part of the disk, and how much rotational inertia does the ring have? Well, the rotational inertia is a small amount, so I use the delta. And it has a small amount of mass, so it's a delta. It's not the whole mass, right? It's a small amount of mass. And also the radius is not the whole disk's radius. So let's draw this line here and put r here. This capital R represents something fixed. Okay, so back to our thought. If I could draw all the different concentric rings, and each ring will have a small amount of mass, and I bet the masses are different, right? If I cut them all the same thickness, then the smaller rings will have less area and less mass. So if I could reconstruct the entire disk by first cutting it into concentric rings, and then figuring out for any ring how much rotational inertia that ring has, and then I can sum up all the rings if I know any ring. This is a generic ring. It's not like a particular location, like half the radius. I didn't really intend to draw that like that. So if I know this ring's rotational inertia, I can add the rotational inertia of all the rings together to produce the rotational inertia of the disk. So that was my goal. This delta I is the rotational inertia of the ring. So let's find out how much mass this ring actually has. So let's first find out this delta m. And we know that the mass is proportional to the area. So if I say that the delta m somehow has area delta A, it's also small, and then multiply by a surface density. So an area density sigma sounds like S, right? S is surface, right? Surface density, how much mass per square meter, right? So that will convert the area into mass. And for area, if I look at this ring, if I make it thin, fairly thin enough, I can just cut it open and straighten it out, and just pretend that this, instead of a ring like this, curves, I just straighten it out into a flat, thin strip. And the strip has what area? The length of the strip is the circumference of this ring, and the width is the width over here, which I can call delta R, right? The change, the increase, or the range of R that changes across. So I cut it, and I straighten it, so I get this. Okay, hopefully I draw long enough. Don't blame me for not getting exact lengths. I'm just doing a schematic. So this is still that thing, and over here this length is the circumference of the circle, the ring, so 2 pi lowercase r, and this dimension is just delta r. So delta area is 2 pi r delta r. Alright, so let's go back here and replace that delta A. 2 pi r delta r times sigma. And if we decide to cut the ring really thin and push delta r to 0 with the limit, then we do this, we get dm. Alright, so dm is equal to, this will be a dA, but don't worry about that, just turns this into a dr. So 2 pi sigma r dr. So that is the mass. And recall that for this much mass, a ring has this much rotational inertia. So the total rotational inertia should be the integration of the rotational inertia of each ring. So this is disk. This is each ring. Alright, so let's find out. as we said, this delta I is equal to delta m r squared. Then di should be equal to dm times r squared. R squared not going into a d because shrinking the width doesn't shrink the radius, right? What's shrinking with it is this delta r shrinks and delta m shrinks with it. So back here, so this is dm times r squared. And we're replacing dm with this. So we have 2 pi sigma. We have r squared. We also have an r, so r cubed dr. And now we can finally specify where to go with the r. So we're actually starting with a very small ring right here. And then we increase to a slightly bigger ring, bigger, 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 all the way up to this big ring, right? So r should go from 0 all the way up to capital R. So that's where our limits are, from 0 to capital R. This is a very easy to do integration, right? So we have 2 pi sigma r squared integrates into r to the 4th power over 4 and evaluated between 0 and the capital R. So 0 goes into that and it gets you 0. That just replaces lowercase r with uppercase r. So you can divide out if you want. So you have pi sigma. Here you have a 2 r to the 4th power. Okay, so we're not entirely done yet because we want to get rid of this density here. So what is density? We know that density is the total mass over total area. Right, so total mass is m, total area of that disk, pi capital R squared. So if we plug this in, then we can get our final answer. The I is equal to pi over 2, and that sigma turns into m over pi r squared. We also have r to the 4th power. Pi divides out pi and r squared, and this goes into squared. We still have 1/2, we have m, we have r squared. So this gets us 1/2 mr squared, which is what we were expecting for a disk. Thank you.